Okay, let's do a conservation of energy problem now between point charges. A proton is fired from far away. As we read, let's recognize that far away means the distance is really big, approximately infinity. It's fired towards a 1 millimeter diameter glass sphere. So from here to here is 1 millimeter. So our proton is far away, it's shot towards this glass sphere, it has some initial velocity. The glass sphere has a charge of 100 nanocoulombs. What is our initial speed vi so that our proton just reaches the surface of the glass, so it just gets to here and touches it? So this is the initial situation. Our proton is being shot towards the glass. Our final situation is that the proton touches the glass and it comes to a stop. Okay, comes to a stop because it just reaches. We know that energy is going to be conserved between the two, so that our initial energy is going to be equal to our final energy. Let's write down our expression for conservation of energy. So E final, our final energy down here, kinetic plus potential, equals our initial energy plus work done by non-conservative forces. There are no non-conservative forces. So our final kinetic energy plus our final electric potential energy is our initial kinetic energy plus our initial electric potential energy. Let's think about what each of these terms are. Let's plug them into the equation and see what we get. Let's start with K final. K final means the final potential energy of both of these things. 1/2 times the mass of the proton times Vf squared plus 1/2 times the mass of the glass times Vf glass squared. The glass is initially and finally not moving, so that's equal to 0. Proton is finally not moving because it just reaches. Okay, so that wording tells us that our final velocity is equal to 0. So our final kinetic energy is equal to 0. What about our final electric potential energy, UEF? Well, our electric potential energy is the energy of interaction between our proton and our glass sphere. So it's going to be K times the charge of a proton times the charge of the glass sphere divided by the distance between the centers. So it's the distance between the center of the proton and the center of the glass sphere. Now, a proton is really very small. So RF is about equal to the radius of the glass, which is 0.500 millimeters. Because a proton is such a tiny radius, it's incomparable to 0.5 millimeters. Okay, so there's our expression for our final electric potential energy. Our final kinetic energy was 0. Let's go to our initial terms. Our initial kinetic energy, Ki, is initial kinetic energy of the proton. We said that had an initial speed of vi, so I'll use that same notation here, plus the initial kinetic energy of the glass sphere. I'll call that initial glass squared. The glass is not moving, so that equals 0. So we're left with 1/2 times the mass of the proton times V initial of the proton squared. Our initial electric potential energy is equal to K times charge of the proton times charge of the glass. Keep getting my G's and my Q's mixed up. Divided by our initial energy, or our initial distance between the centers. Remember, that's far away. It's so far away that this is close to infinity. It's a very, very big number. So our initial electric potential energy is equal to 0. So this one is equal to 0. Okay, so we're going to put this in for our kinetic, we're going to put this in for our potential, and we're going to solve our problem. This page is a bit full, so I'll get a piece of scrap paper. So let's put all of our terms in our equation. So KF plus UEF equals KI plus UEI. Let's cross out the things that are 0. That one is 0, and this one is 0. Our UEF, let's see, I think we can see that all on the screen here now. Maybe I'll just move the page a bit. Our UEF, let's copy that one down. K times the charge of a proton times the charge of the glass sphere divided by RF equals our initial energy. That was 1/2 times mass of the proton times the initial velocity of the proton squared. I want to solve for VI, so VI squared is going to be 2 times K times the charge of a proton times the charge of the glass divided by RF. Also got to divide by the mass of the proton. To get our V, we've got to take the square root. Okay, I think I'll just write my values over here on the side. K is 8.99 times 10 to the 9 newtons meters squared over coulombs squared. Q of the proton is positive of our fundamental charge, 1.6 times 10 to the minus 19 coulombs. Q of the glass sphere was 100 nanocoulombs. That's 10 to the minus 9 coulombs. Mass of a proton, 1.67 times 10 to the minus 27 kilograms. And our final distance between our two charges was about the radius of the sphere, 0.5 millimeters. Put all those numbers in our calculator, we should get 1.86 times 10 to the 7 meters per second. It's pretty fast, but it's less than the speed of light, so we're okay with this answer.